I'm pretty proud to say that the first paper published on 3D printed chromatography media was published by Professor Fee, Suhas Navada, and myself, as we were in New Zealand at the University of Canterbury in Christchurch. The paper was published in 2014, in January 2014, and it was a very interesting experience, that one, because we started to conceive the idea about 3D printed stationary phases in 2012 as 3D printed became mainstream. And it was pretty exciting to see this transition from concept idea to having real artifacts, experimental models that could be experimentally tested in just a few months' time. That eventually enabled us to 3D print for the first time a stationary phase with ordered morphology, to test it experimentally by Suhas Navada, and eventually then write our first publication. Well, I think there are many different aspects that 3D printing is tackling at the moment in the chromatography arena. In our case, with 3D printing of stationary phases with ordered morphology, which is still followed by Conan Fee in New Zealand and by myself in Edinburgh. There are other groups, for example, GERDASMET, that is instead trying to 3D print at extremely high resolution stationary phases using two-photon photopolymerization, which is an extremely refined 3D printed technique. But there are also other groups that are instead working on different aspects. For example, the column housing, the cartridge where to have your chromatography columns, especially the group of Professor Brett Paul in Australia, in Tasmania, where he tries to miniaturize at the same time columns using some specific architectures, geometries for the column holder. And then there are other groups that instead work on different separation methods, for example, planar chromatography, thin layer chromatography, there is solid phase extraction, and there is a whole set of other things where 3D printing can be particularly useful in the entire process line in a chromatography operation, starting from sample preparation to injection to, of course, the chromatography column, but also the hyphenation with MC or other detectors. So there is a whole range of things where 3D printing can be absolutely useful for the separation science. This is a very good question, and my feeling is that the chromatography industry is relatively conservative. With the 3D printing approach, we are already giving a particularly strong revolution, a new challenge and a new product. So I don't feel that if we want to remove as many barriers as possible to enable the commercialization of 3D printed chromatography columns, then we have at least removed a few barriers. One of them is material. So I would say that the best approach, in my opinion, is to employ commercial materials that are already well accepted by industry, well accepted by regulatory agencies. So I feel it's the important aspect is instead into the 3D printing by itself, rather than in the material. The fact that you can 3D print specific morphologies that are geometries that are perfectly suited for your chromatographic operation, whatever that can be. So I think that is the real challenge, and also the good opportunity for 3D printed chromatography columns. Right, now the main challenge there is the compatibility, is to create some sort of compatibility between the materials that are currently used in chromatography and the materials that are instead processed by 3D printers. And there is a disconnect at the moment. Even if we can consider that some materials are 3D printed and used in chromatography, for example, silica, hydroxyapatite, or methacrylate materials, polystyrene materials. All these materials are printed at the moment, and we know that they are extremely useful in chromatography in one way or in another. The point is that 3D printing companies tend to develop their methods, their 3D printing methods, to obtain a solid, fully strong material that has got improved mechanical properties. In our case, we want a porous material. Quite often we employ hydrogels, which are not necessarily the target of 3D printing industries. So there is that disconnect that needs to be overcome, so to enable a true employment of 3D printing chromatography. There are two main methods to do that. The first one is to use the same materials that are employed in chromatography and develop a new 3D printing technique, or to use a commercial 3D printer and develop a new material that is compatible with that 3D printer. We tried in the past 7 years, we tried both approaches, and I feel that the easiest approach, at least for us, is to develop new materials using commercial printers. And there is a simple reason for that at the same time. Most of us is either a material scientist or is a separation scientist with not too much background into the mechanical engineering or electronic engineering aspects that are fundamental for the development of a 3D printer. At the same time, we can see that 3D printing is evolving so fast that I imagine that most of the roadblocks and hurdles that we see for the 3D printing of chromatography materials will be solved by other people. So I feel that that approach of developing materials, focusing on materials, is better suited for our background. Well, the reason we started exploring ion exchange is because there are commercially available chemicals, that incorporate specific chemistry that is useful for chromatography. There are, for example, methacrylate monomers with carboxy functionality, with quaternary amine functionality that are or DEAE functionality that lend themselves for creating a formulation, a material that can be 3D printed. And once you 3D print, you obtain an ion exchange chromatography material. This concept is particularly interesting and exciting because you enable the 3D printing of a chromatography column in only one simple step, where you don't have a post-functionalization so that you can introduce the chromatographic ligand. And that is the first point to enable the concept of 3D printing your own chromatography column. I must say that there are other chemicals commercially available that incorporate other kind of functionalities useful for chromatography, for example, hydrophobic interaction ligands. Or helic in other words, or other chemical moieties that can then be modified to incorporate an affinity ligand. So there is a whole lot of other things that can be done with these commercial materials. So that, again, it's a convenience. It's a matter of convenience. You get what is available at the moment, commercially available, and you try to exploit it to bring it to a next level, to obtain a value with much added value. Well, in general, chromatography stationary phases are nothing but some solids with some channels next to them, and you flow something through the channels, and some species in the fluid will absorb into the solid. So that is a general principle that is not specific for chromatography. There are other techniques in the industry that exploit exactly the same mechanisms. Let's say, for example, bioreactors or catalysis in general. There is also carbon capture. And these are all aspects that are interesting to me. So at the moment, we are exploring immobilized enzymes bioreactors, biofilm bioreactors on these 3D printed structures. And with other colleagues at the University of Edinburgh, we are also considering to 3D print monolithic porous structures for the sequestration of CO2 from the atmosphere to mitigate global warming problems. if I go back in time and I think about the first separation enabled by Martin and Singe in the 40s, and I consider that it took 20, 30 years for that discovery to be eventually commercialized, then I should say 20, 30 years. In reality, things are moving so much faster today, especially in the 3D printing area, where you get a new 3D printing method almost every month. And this is pretty exciting to see how quickly it is developing. So my estimate would be definitely one order of magnitude smaller, and I would say something in the order of 3 years. You will see this chromatography column commercially available. Yes, I think that the important message that I would like to send is that at the moment there is so much to do into this area of 3D printing and separation sciences in general, chromatography specifically. And I feel that at the moment there is still just a bunch of people, a handful of people working in this topic. And there are so many challenges to be solved that can be turned into new opportunities. So I think my take-home message is get inspired by what you can see, by what is that 3D printing can enable, and jump into this topic because it's truly, I think, revolutionary. It has got the potential to change the way we see chromatography and separation sciences in general.